Okay, thanks, Akash. So, as I said, like the first part was more of a leisurely introduction and a discussion of monotonicity testing and directed isoperimetric theorems. And so, in the second part, what I'll try to do is I'll try to get into some of the proofs. So, I won't prove, maybe any of the statements in full glory, but I'll try to give some technical detail about things, and we'll see how far we get and whether I can tell you about how the KMS proof goes. So this is really about proving the directed isoperimetric theorems. So is my writing clear? Can everyone see the paper and what's being written?
I think it's clear.
Okay, all right. And again, needless to say, please stop me at any point if there are any questions. So let's start with the simplest the directed Poincare statement, which was basically just this sort of directed influence is omega of the distance to monotonicity. And so I will show you the proof here that was given by GG LRS. And this is like a very nice argument, and this is called the switching argument, which makes an appearance in many aspects of of monotonicity testing and in a lot of combinatorial tricks on the Boolean hypercube. Okay, so here's how the proof of the statement goes. So we're going to start from this function f. So again, remember f was this Boolean function on d dimensions. And I'm going to perform a series of transformations, f going to f1, going to f2, going to f3, so on and so forth, going up to fd, and fd is going to be the function g. Now the promise is that g will be monotone. And so hence, epsilon f is going to be at least the distance of f and g measured in Hamming, and this by triangle inequality, well, no, I'm doing this the other way around, I'm sorry. So, sorry, I got my inequality is the wrong way. So the distance to monotonicity is at least the difference between any function, between the function and any monotone function. And by triangle inequality, I can just write this as I d minus 1 f of I minus 1 fi 0, right? I'm just saying that I could look at the successive differences between these functions, and I know that the sum of those successive differences is at least is greater than equal to the difference between f and g, and the difference between f and g is greater than epsilon. And what we will show is that this is going to be, up to some scaling, up to some normalization, this is going to be the number of violated edges. Okay, so this is the overall approach. And so what is the process that goes from fi minus 1 to fi? This is something that I will call switching in the ith dimension. So switching in the ith dimension. Let me zoom out a little bit. Okay, so what is, sorry, just give me a sec. So the switching process will do the following. It's going to take every edge, directed edge, xy along the ith dimension. So remember, I is a dimension here. So for every edge on the ith dimension, if the function value is a 1 and 0, it is going to change that. It's going to fix that violation or switch it to a 0 and 1. So it's going to do this for, if you look at the Boolean hypercube, all I can draw is 3 dimensions. I look at some dimension I, so I look at all of these edges. And for any edge that's a violation, I swap the values. And I do this for all the edges in parallel in one go. So this is the switching. Technically, it's an operator. It's an operation on the function. When I switch, I will go from fi minus 1 to fi. So the way this process works is that from f to g, it's, switch on 1, switch on 2, switch on 3, so on and so forth, until we switch on the dth dimension. Okay, so what this is doing is that I'm going to fix the violations in each dimension in order. Now, I'll pause here and I'll let you think about it. Like there seems to be an issue. And the issue is that, let's say I switch on one dimension. So I fix the violations in that dimension. But now if I switch on a different dimension, I may reintroduce violations in a previous dimension. Right? So there's no reason why, this is not clear that if I do this process, at the end, I'm going to end up with a monotone function. Is any questions? Hopefully that comment was clear. Okay. So I'm going to write a claim here. And with this claim, the entire proof will follow, which is switching of the ith dimension. I said switching on, does not increase the number of violated edges in the jth dimension, where j is not equal to I. Right? So what this says is, this is the key claim, that if you switch on one dimension, you cannot increase the number of violated edges in any other dimension. Now from this, it should be clear that this process leads to a monotone function, because I switch on 1, switch on 2, switch on 3. Now by the time I reach here, there are no violations in dimensions 1 and 2. Moreover, further switching cannot increase the number of violations in dimensions 1 and 2. Hence, by the time I finish this process, I have a monotone function. Okay, any questions about that? I'll pause here and allow you to sort of soak in all the notation. Okay. And so now what it remains is just to prove this claim. And the proof of this claim is, unfortunately, it's basically just a case analysis. And I might draw out a few of the cases, but not all of them. So what happens is you switch in the ith dimension, and you want to see what happens in the jth dimension for j not equals to I. So essentially, it's all operating on squares. So if this is the ith dimension, this is the jth dimension, we're really operating on squares. So we're saying if we switch in the ith direction, excuse me, could we introduce a violation in the jth dimension? And you basically draw out the case analysis, and I'll just draw out a few cases. Suppose this is a 1, 0. And I don't know what these are. for all possible values here, I'll show you that when I switch on this dimension, I am never going to increase violations in all the dimensions. So there are basically 4 situations to draw out over here. I could have 1, 0, 0, 0. I could have 1, 0, 1, 1, 1, 0, 0, 1, and 1, 0, 1, 0. Right? These are the function values here. I'm assuming that one of these edges is 1, 0 because there has to be some switching. If no switching happens in the square, then of course nothing will change in dimension. So what happens when you do the switching over here? This is going to become a 0, 1, 0, 0. So the number of violations in this dimension, in the jth dimension, there was 1 violation here, and there is still 1 violation here. Right? This edge, violated edge, moved over there. So it never increased. If I'm in this situation, then there were 0 violated edges here in the jth dimension, and it remains to be 0. Now in this situation, you go 0, 1, 0, 1. So there was 1 violated edge in this dimension, and there are actually 0 violated edges in this dimension. It decreased. And over here, there were 0 violated edges to start with. And after doing the switching, there are 0 violated edges over here. So what happens is in the jth dimension, the number of violated edges has never increased. It has always stayed the same or decreased. And so you could do the similar picture when the top edge is a 1, 0 and you work it out, it's exactly the same. So what this says is that if you switch on the ith dimension, you do not increase the number of violations in the jth dimension. Any questions about this statement? Okay, very good. So what this means is going back to our picture over here. Remember, we went from F to F1 to F2 to FD. This is equal to G, and this I'm just going to call F0 for convenience. So the first claim is that G is monotone, right? And the proof is quite easy here. We switched on all dimensions. Now the other key claim that we need here is that if I look at what is the difference between f of I minus 1 minus fi, I claim that this is at most 1 divided by 2 to the d of the number of violated I edges in F, not in Fi. So remember that this quantity is actually equal to 1 divided by 2 to the d of the number of violated edges, I edges in Fi minus 1, right? Because that's exactly what this is doing. It is switching on Fi minus 1, not on F, right? At any intermediate stage here, you're switching on Fi minus 1. So the amount of change that it does is really the number of violated edges in Fi minus 1. But Fi minus 1 was obtained by switching on multiple dimensions, and switching never increases the number of violations in a new dimension. And so what this
times 2. It should be times 2.
Times 2, yeah, okay, times 2. Times 2, because you mean the changes on both ends, correct? Yeah, times 2. So you get 2 divided by 2 to the d of the number of violated I edges in F, right? And this is the key, and this is by the switching claim on switching. Okay, and so now our story is complete. I'll say this is at most epsilon F. This is at most, by triangle inequality, all of these successive differences. And by our previous claim over here, this is say 2 divided by 2 to the d, the sum over I going 0 to d minus 1 of the number of violated I edges in F. And this is exactly the directed influence of F. And so what we get is the directed influence is at least epsilon F divided by 2. Okay? And this is the proof of the Poincare inequality. Okay, so let me walk over this again, and then I'll pause and answer any questions that you may have on this. So the directed Poincare inequality said that the directed influence is at least the distance to monotonicity. And the way we do this is by doing what's called a switching argument. We start from F and we excuse me, we successively transform F into F1, F2, F3, so on and so forth up to Fd, where Fd is equal to G. We will show that G is monotone. So G is monotone, so the distance between F and G is going to be at least epsilon F. That's by the definition of distance to monotonicity. And then what we get over here is that the difference between F and G, that by triangle inequality, is just the differences of the distances between every successive pair Fi minus 1 to Fi. So what is the switching operation? I basically look at all edges in the ith dimension, and if it's a violation to monotonicity, I switch it. Now this is actually quite interesting, that you could fix this violation by maybe making both of them zeros or both of them ones. But that doesn't work in the proof. Like, it's actually the swapping which actually will make the proof work. So you swap it. And so the way to go from F to G is you switch on 1, switch on 2, switch on 3 successively all the way up to D. The first claim is that you switch on the ith dimension and it does not increase the number of violated edges in the jth dimension for a different dimension. This is the key claim here, which it's just by a case analysis, but this is the key claim, because once you have this claim, then it should be clear that when you successively apply the switching operation on all the dimensions, you end up with a monotone function, because when you switch on one dimension, there are no violations in that dimension. You switch on that a different dimension, you don't increase the number of violations in that dimension, so it remains 0. The proof of the statement was just a fairly simple case analysis, where when you're looking at two dimensions together, you're looking at a square. So all you need to do is to say that you have a square in I and j, you switch on I, and the violations in j will not increase. You work out the case analysis, you can prove this. So what we get in the end is that G is monotone because we switched on all the dimensions. And the second important point is when you switch on the ith dimension, the number of changes you make is actually, I should say, 2 times. It is 2 times the number of violated edges, right? Because every time you have a violated edge, you change 2 points. So it's exactly 2 times the number of violated I edges, these I-dimensional edges, in Fi minus 1, in the function that you're switching. But as we said, when you switch on dimensions I1 to I-1, you cannot increase the number of violated I edges. So the number of violated edges in the original function is greater than or equal to this quantity here. And so then we get that when you switch on the ith dimension, the amount of change is the number of violated I edges in F. And so then you chain it all together and you get the result, right? So this proves the Poincare inequality. It's a fairly short proof. Any questions about this proof? Okay, good. Sorry, Akash, can you tell me how much time is left? I'm just timing myself and I didn't do the time change correctly.
So you have around 40 minutes.
40 minutes? Okay, good. Yeah, good. So any questions about this? Okay, so this is, again, it's like a nice exercise, not very difficult to prove. And this was actually the original proof as given by GGLRS. So I think initially they had an even more complicated proof, and then in their journal version they had this very clean, simple proof, very beautiful, elegant statement. Now I want to point out something here, which is one of the biggest difficulties one has in any proof in property testing is how do you bring the distance to the property into the equation somehow. And the way that they do it here is by actually transforming the function from f to g. And so you can basically get this inequality here. And this is, of course, how you bring the distance to monotonicity into the equation. Now, what I'm going to show over here is, and I'll try to work it out in as much gory detail as possible. So I will, okay, I'll make a comment about hypergrids over here. So essentially, a similar argument holds for hypergrids. It ends up being a little bit more technical, but essentially what you get is there is a sort operator on the line, which is sort of, what you might think is the obvious. What the sort operator does, if it's got a bunch of ones and zeros, it basically moves all the zeros to one end and moves all the ones over here, right? So this is the sort operator. So the sort operator, again, is, you can kind of think of it as the generalization of the switching operator, and you kind of apply exactly the same style of argument. Now, what you get is a little bit more, the final result or the final bound that you get, the theorem you get is that, so what is and this is sort of relevant or to how you construct isoperimetric theorems over the hypergrid, where it's more complicated. There was a notion of influence here, which is omega epsilon. And here, I'm going to write something here, and then I'll tell you exactly that summation I going from 1 to d of epsilon f comma I, that this is omega epsilon f, where epsilon f comma I is the average distance to monotonicity of the I-dimensional lines. Like if you look at any line, you have a function, you can look at the distance to monotonicity, you look at the average distance to monotonicity of I-dimensional lines, and you sum this over all the dimensions, and then you get omega epsilon f. And if you note that in the hypercube for the hypercube, is exactly equal to, I mean, up to a constant is basically the number of violated I edges divided by 2 to the d. Again, up to like a factor 2 probably. Okay, so this is how you generalize for hypergrids. I won't go into the proof here, but essentially, again, you can follow a similar strategy, and essentially, you can again prove the statement where switching on the ith dimension. Now, you don't do the number of violated edges. You have to argue about the distances there. It's more complicated, but essentially, the idea goes through. What I'll actually go over is proving the directed Margulis theorem. So this is simpler than the Koopmans-Safra proof. So this was by, so I'm going over essentially the proof ideas we had when we got the d to the 7/8 tester. So let me remind you what the Margulis theorem is. So that says the influence times gamma is the square to the distance to monotonicity, and this was the directed vertex boundary. So how do we prove this statement? Now, at a philosophical level, it's quite different from how you bring in epsilon f over here. And we use a different notion called, we're going to start with a different notion called the violation graph. So this is to get a hand on a convenient characterization of the distance to monotonicity. So what is the violation graph? The violation graph is G. So I'm just talking about the hypercube here. So I'll just do 1 to the d. But this violation graph actually holds for any partial order, where I basically put an undirected edge between xy if xy is a violation to monotonicity, but this not all edges, not just an edge. So this is for any pair. So if x is less than y and f of x is greater than f of y, then I put this edge here. So note that the number of edges here could be much larger than the number of edges in the hypercube. This is not an edge of the hypercube, but rather an edge of the violation graph. So this, one has to be a little careful when I say edge. Usually I mean edge of the hypercube. I will refer to these as violated pairs. Which I will just refer to as a violation. When I say violated edge, I'm referring to the edge tester and the edge, but I'll call these violated pairs. Okay, so let's take the violation graph. So this is some set of edges. And so consider any vertex cover. Now, what do we know about any vertex cover? That any edge has to have at least one endpoint in the vertex cover. Like, you cannot have edges of that form. So if you remove the vertex cover, then you remove all edges. This is the same thing as saying remove the function, or technically delete, remove or delete the function on a vertex cover. Then what you will end up doing is you remove all violations. Right? These two statements are equivalent. If you remove the function on a vertex cover, you end up removing all the violations. Same thing as saying if you remove a vertex cover, you remove all the edges. Okay, any questions about this? And indeed, what this means is that the size of the min vertex cover is an upper bound on the distance to monotonicity. And indeed, actually turns out to be equal. It's actually equal. So what you can get is that, and again, I'm just talking about the hypercube in this calculation here, but it works for any domain. Works for any domain. So the size of the min.
Seshadhri, just one moment.
Yes.
Where? Yeah, could you please re-explain the part what does removing the function on vertex cover imply for removing all violations? How does
Yeah.
that work?
Okay. Yes, certainly. So let me maybe draw a picture to do that. So here's my hypercube, and let's just say the vertex cover on the violation graph is this. Right. So this is the vertex cover. What does this mean? It means if you take any violation to monotonicity, take any xy where x is less than y and f of x is greater than f of y, then either x or y must lie in this set. So let's just say maybe x lies in this set and y is somewhere outside, or maybe y could be inside the set. What this means is if I say I made the function undefined on the vertex cover, so make the function undefined on the vertex cover. I just like delete the values. So now you have this partial function. There are no more violations to monotonicity. Violations to monotonicity. Of course, this is an undefined function. Then what I do is I go back and define the values. Basically, you can do a topological order of the DAG, and you can define the function values in here so that you'll maintain monotonicity. So go back and redefine to create a monotone function. So this step, there's a little bit of work involved. Work as in, it's not work, but I mean, you have to prove that you can take a topological order of the DAG, and then at every undefined point, you just look at all the previous points and take the max value amongst that. And you can argue that when you finish this process, you will have no violations to monotonicity because you removed all of them when you deleted the vertex cover. Does this answer your question?
Yes, thank you.
Okay. So going back to this, the size of the min vertex cover of the violation graph is actually equal to epsilon f times. It's exactly the distance to monotonicity. You can argue that anytime you change, you have to change a vertex cover. Now what we'll do is, for min vertex cover, we know that this is at most the size of a maximal matching divided by I should say 2 times maximal matching size, right? Because if you take any maximal matching and you take both endpoints, then that is a vertex cover. So 2 times the size of a maximal matching is at least the size of the min vertex cover, which is at least epsilon times 2 to the d. So taking all of this behind in this graph, what we get is this crucial lemma here, that there exists a matching of violated pairs, like a matching M of violated pairs, where the size of M is at least epsilon f2 to the d minus 1. And this again holds for any domain. So technically it's just the domain divided by 2. So what we have is now a different hook into talking about the distance to monotonicity, which is this matching of violated pairs. And we're now going to use this matching to help prove the directed Margulis theorem. Okay, so I'm going to, again, just to write this out. So what is this matching? It's x, y, where x is less than y, f of x is greater than f of y. At this point, I haven't even used the Boolean nature of it. It's just what it is. And these are all disjoint pairs. And we know that this is essentially omega epsilon f times 2 to the d. Now what we're going to do to prove the directed Margulis theorem is to use this matching. And what I'll actually do is I'll give you two bounds, one for the influence, one for the directed vertex boundary, and we'll multiply them to get our final bound. So the first thing we're going to do is actually get a strengthening to the point. By the way, I should pause and say, are there any questions at this point? Please stop and ask me. All right, I'll assume that most of you are following. Okay, so to prove the directed Margulis theorem, I'm going to take a very specific matching, and that matching is going to help me exploit a lot of, well, I'm going to use properties of that matching to prove this. Okay. So for any such violation matching M, let the average distance of M, so distance is a bit overloaded here, but the average distance of M is equal to the average value of the Hamming distance between x and y, the average where x and y is in M. Okay, so I'm looking at the average distance between the pair. And what I'm going to do is pick the largest M by cardinality with the smallest average distance. Okay, so I'm simultaneously optimizing two things. I have to be careful. So I'm just picking the largest one. I know there exists a large matching of violated pairs. Amongst the ones of the maximum size, I pick the one with the smallest average distance, where the pairs are as close to each other as possible. I'm going to refer to this average distance as R. Any questions about this definition? Okay.
There is a question.
Yes.
Which order? So you first pick the largest, all the largest M's, and among them the one with the smallest.
Exactly. Yeah, so you first pick the largest one. So I want something that has like, which is pretty much a certificate to the monotonicity, but amongst those certificates, I'm picking the one with the smallest average distance. Okay. Now I'm going to actually prove a strengthening to the Poincare inequality. So this is what I will call stronger Poincare. So stronger Poincare is going to say that the number of violated edges, divided by 2 to the d, which was my IF plus. This is actually omega r times epsilon f. Remember, Poincare just said it was omega epsilon f. But what I'm claiming is if you pick the largest matching with the smallest average distance, then you get actually, and whatever that distance r is, you actually get to multiply by r. So if it turns out that the smallest average distance is large, then actually the influence is more than that. Does that statement make sense? And I'll say the statement and I'll come back to it. I'll say it, I won't draw it out right now. But actually, for example, if you take the anti-majority and you try to match the pairs up, the average distance becomes square root t. And so that actually shows that for, well, of course, for that function, you know the bound, but it's consistent with that bound, that you get a square root t improvement over the basic Poincare bound. So the proof is best shown by sort of drawing out a picture and explaining what is going on. And then, the formalism of it is just notation, which I don't think is going to add much value. Once you get the idea, the formalizing is not that difficult. Okay, so what is the proof going to look like? So I'm going to pick some xy in M. So M is this matching that I've chosen here. And I'm going to pick a dimension I that xy crosses. So what this simply means is that xi is 0, but yi is equal to 1. So there's obviously some dimension where the coordinate changes. I'm going to pick some dimension of this form. Okay, and draw this out over here. So this is the ith dimension. And what you get is x is somewhere here, y is somewhere there. The value on x is 1, the value on y is 0, right? Because it's a violation. And because it's in the matching, it's a violation. Okay. Now what I want to do is I'm going to charge each xy crossing the ith dimension to a unique violated I edge. So this is the process which is going to be, which I have to define, but the overall strategy is I'm going to basically charge every such pair which is crossing the ith dimension. Every violated pair in this matching that is crossing the ith dimension, I'm going to uniquely charge to a violated edge. So what is interesting is that for every pair, violated pair, I get to find an edge in every dimension that it crosses. How many dimensions does this pair cross? It's exactly the distance. Okay, I will write this down, but I want to say this out, and then I will repeat myself on paper. I'm going to charge every pair that crosses the ith dimension to a unique violated I edge. So if you think about what happens to a specific pair is going to effectively discover or charge an edge in every dimension that it crosses. And how many dimensions does a pair cross? It's exactly the Hamming distance between them. It's the distance between them is the number of edges it will cross, and you get those edges. So how is this going to work, this process? So I'm going to begin by projecting y down along this dimension to this point S1. Okay, so now let me write some stuff down. So if f of S1 is equal to 1, then S1y is a violated I edge. So I'm done. So suppose I'm not done. This means that the value there is a 0. Okay, now, if I'm going to abuse notation and say S1 is not in M, which means that S1 doesn't participate in anything in M, then what I can do is I can replace xy in M by x S1. This is also a violation, right? Because x is less than y, and all I did was project. I just changed the y coordinate to the I coordinate to 0. So this is also a violation. I could replace this by a violation. I could replace xy in M with xs1 in M, and then I would reduce the average distance of M. That's a contradiction. Why is it a contradiction? Because remember, I picked M with the smallest average distance. So I cannot reduce the average distance. Any questions at this point? Okay. Hence, what must happen? S1 is in M. Or specifically, there is a pair S2, S1 in M, where S2 is less than S1. There's a violation because it's a violation with this. So there's some S2, and the value there is 1. So just to maybe draw out the violations in the original graph, I'm going to use this marker. There is a violation over there. There's a violation over there in the original graph. So let me sort of put the value over here. Now what I can do is I'm going to play this game by projecting this back up. So I get to S3. Now I'll just repeat the argument again over here, just for clarity. If f of S3 is equal to 0, then S2, S3 is a violated I edge. And then we're done. We've discovered a violated I edge. If S3 is not in M, then I do something that I call a rewiring. So I replace xy and S2, S1 in M by x S1 and S3, x S1 and S3y, x S1 and S3y. And again, what happens is that the average distance reduces contradiction. So what you will get is that again, S3 is in M. So S3 will have a value of 1. And we end up at some S4 with a value of 0. You project to S5 and you repeat this argument. Okay? So let me write out a few things and then I'll come back and summarize. So what happens is by repeating this argument, the process can only terminate by encountering a violated edge. And moreover, each pair that is a violated pair leads to a unique violated edge. This requires a bit of work to show that, but basically the point is that because these are all matchings, this red thing is a matching, the projections are a matching, and we're essentially taking alternating paths. So we're taking alternating paths of these two matchings and we're following the alternating paths. And when you follow the alternating paths, you can show that every violation must lead, every violated pair leads to a violated edge in that dimension. So I will just repeat this argument again. So we want to charge each violation xy to a violated edge that is crossing the dimension. The way that this works is you take xy, you project down, you get S1. Now if S1 had a value of 1, then this is already a violated edge. Hence the value is 0. But if the value is 0, then actually x S1 is also a violation of monotonicity. So if S1 was not in the matching, then you could match x to S1 and you would reduce the average distance. Since we started with something that minimizes the average distance, S1 participates in the matching and is matched to S2, which has a value of 1, right? Because that's a violation. So S2, S1 is in the violation matching. That's why I marked it in red. Let's now project S1 back up to S3, and you repeat the same argument. You say, well, if S3 has a value of 0, well, then we've discovered a violated edge. Therefore, the value at S3 is 1. And if it did not participate in the matching, then you do a rewiring. You say, you can basically replace XY and XS1 by XS1 and S3Y. And so the complicated part really in this argument is as the path becomes longer, you basically have to write out exactly what the rewiring is, but the philosophy is exactly the same. You'll basically rewire in, once you write out the pattern one more time, you see the way in which you rewire. And so you do this rewiring and you reduce the average distance. Now, because the average distance was minimized, and this was key, we chose the minimum average distance, we know that S3 has to be matched to some S4. And if you keep iterating this argument, it has to terminate somewhere. Because note that these are matchings and we're taking alternating paths, it will never cycle into itself. Any questions about this? It's a bit technical, but any questions?
I think that's okay.
There seems to be some superficial similarity maybe to canonical paths. Way of not really.
Sorry, canonical paths. You mean like a symmetric, like a chain decomposition, or?
No, like as a method for proving, isoperimetric-like inequalities, like for Markov chains. But here, the reason I was saying this is because of this thing of charging each. The violation graph looks like it's like essentially like a transitive closure kind of a thing, right? So it's like, or not like a transitive, it's like some kind of a long distance graph. and you're trying to charge each of those sort of paths to one edge.
Yeah, I see. But in some sense, it's not really a path, but a pair.
Uh-huh.
Like the fact that it comes from a path, somehow the path is not relevant here. But that is an interesting thought. I've never thought about that, there's some connection to that. This seemed more like, I mean, like the way that this proof, how the way you get a unique charging is because there is these two matchings, like you take the alternating paths and cycles formed by these two, by the symmetric difference of two matchings. And so it seems something about that structure. I will admit that there are some aspects of this proof that are mysterious. I mean, it works and it actually generalizes to many product domains. Yeah, but that's an interesting thought. Yeah.
Okay, thanks.
And so I'll just, sort of write out that, so we formalize by taking the alternating paths formed by the matching M and the projection, the I-dimensional projection, and so when you do this formalization, what you'll get is that basically the number of violated I edges is at least the number of pairs in M crossing dimension I, and so what you get is that the total number of violated edges is at least the sum over all x, y, and m of the Hamming distance between them, and this is exactly r times epsilon f times 2 to the d. I mean, up to some constant, up to a constant. And so by dividing, you basically get, this is omega r. Maybe there's like a divided by 2, there's a constant there. And so you get this strengthening of the Poincare inequality. So Akash, I have about 5 minutes left, maybe even less.
You can take up to 5-6 minutes, sure.
I'll take about 5 minutes and just wrap up. So what I gave you was one piece. The second piece the theorem that we get over there is that, so this was the edge boundary. And what it says is when that minimum distance matching is really far, then the edge distance increases. But when it's really close, well, then you start going back closer and closer to Poincare. But what we'll prove over here is actually the opposite behavior. So for that min distance matching, what we can prove is if that distance is really small, the vertex boundary must be large. And this is the exact trade-off between these. What was very fascinating about this proof is that it explicitly gives you a parameter that is trading these off, which is the distance of that minimum, the minimum distance matching. The minimum distance violation matching, that distance gives you the trade-off. And this was a sort of a surprising aspect of this. So Deepanam and I have a recent paper relating this to some kind of flows, but we still don't understand this completely. The proof of this, now clearly I don't have time and I don't wish to take up more time, but the proof uses a statement called the Lehman-Ron theorem. on disjoint paths in the hypercube. And so I'll just give you a quick cartoon proof. So instead of taking a dimension by dimension view, you can take a level by level view of, this is the level view of the hypercube. And then if you look at your matching M, so this is the matching M, has, let's say, pairs here and here where these have value 1 and these have value 0. What you can do is you can use this theorem to find these disjoint paths, and the disjoint paths will discover something on the boundary. And so you use this to discover paths on the boundary. You have to iterate over this argument, and there are some details, but then you can prove this statement here. And when you multiply them together, then you get Margulis. The R disappears, and you get epsilon f squared. This is the proof of the Margulis theorem. And I'll just make a comment that that the nice aspect of this proof is that the entire proof generalizes to what is called the augmented hypergrid. So this is where if you take n to the d and you look at any line and you basically put an extra edge between all power of 2 differences, 2 square, 2 cubes, so on and so forth. So if you augment this, then in this structure, in this augmented structure, directed Margulis holds. And this is the first time that we were able to get a little O of D procedure for any hypergrid. So this basically led to a D to the 5/6. I mean, together with some other results, you could use this to get an O of D to the 5/6 tester for monotonicity on hypergrids. And of course, the question is, what about the directed Talleyrand theorem? Well, for that, you'll have to invite me again, and I can give another tutorial. And the next time I come by, if you're interested, I'll be more than happy to tell you about how to prove the directed Talleyrand theorem. The proof there is much more difficult and much more involved and uses a very different set of techniques. But with that, I think I'm out of time, so I'll end here and I'll take any questions that you have. And again, I thank you again for inviting me and attending this talk.
Thanks, Seshadhri, for staying up this late in the night. So Seshadhri, I have a question for students' benefit. Could you sketch the gamma f plus proof once again from Ramanujan?
Oh, this proof over here. Well, actually, I didn't give any details here. So the way that this works is, so you have this matching M, and I'm going to partition M into Mij. So I'll write this out over here. So Mij is actually equal to all pairs xy, where the Hamming weight of x is I and the Hamming weight of y is j. So what this is saying is I'm basically taking two levels of the hypercube. and I'm finding some subset here. And there is a matching between these two things, right? Basically, I'm just partitioning the matching into these. Now, the Riemann-Rohn theorem says that when you have any matched sets in, I should say the values here are 1 and the values here are 0. The Riemann-Rohn theorem says that if you have matched sets between any two levels, then actually you have vertex disjoint paths between them. So every vertex disjoint path is starting from a 1 and going to a 0. So at some point, it has to cross from a 1 to a 0. So there's going to be some edge in here that's a 1, 0 edge. Now, immediately, you have found something that now belongs to the vertex boundary. So there's a 1, 0 here, 1, 0 here. So then you start discovering these things that are on the vertex boundary. Now, what you need to be careful about is you iterate this argument, but maybe there is another level here. And when you find these paths, you rediscover the same point. So you have to be a little careful to see how many times do you rediscover a point when you iterate this argument. And there's a relatively straightforward argument that shows that you can set it up so that the number of times you rediscover is exactly the minimum distance of the matching. And sort of that's why you divide by R. So when the minimum distance is small, you rediscover the same boundary point fewer times. And that's sort of the argument.
Other questions? So I guess we should really let Seshadhri sleep. So thank you very
Fine.
much, Seshadhri, for coming here, and let's all thank Seshadhri again. Okay, Seshadhri, thank you. So yeah.
Thank you very much. Thank you.